There is a question that most
At
people
their
never
core,
think to ask.
these two extreme phenomena
Not because it is too
reveal
difficult,
identical underlying
but because the
geometries.
answer seems obvious. Where did everything come from? The stars, the galaxies, the atoms in your body, the laws that hold them together? Where did all of it begin? For most of human history, the answer belonged to religion or myth. Then science arrived, and the answer shifted to the Big Bang, a moment roughly 14 billion years ago, when everything that exists exploded into being from an inconceivably small and dense point. And that, for most people, is where the story ends. The universe began. It expanded. We are here. Case closed. Stephen Hawking spent his entire intellectual life refusing to close that case. And what he found, at the edge of his equations, at the boundary between known physics and the void where physics breaks down, was that the question of where everything comes from and the question of what happens inside a black hole are not two separate questions. They are the same question, asked from different directions. Black holes do not merely destroy, they reveal. And what they reveal, according to Hawking, is the hidden architecture of how existence itself begins. To understand why Hawking arrived at this conclusion, you need to understand what a black hole actually is, not as a popular image, but as a physical object with precise mathematical properties. A black hole forms when matter collapses under its own gravity to such an extreme density that it warps the surrounding space-time beyond recovery. At its boundary, the event horizon, gravity becomes so severe that escape velocity exceeds the speed of light. Nothing that crosses this threshold can return. Not matter, not radiation, not information. At least, that was the assumption before Hawking changed everything. In 1971, Hawking proved something that seemed at the time like an elegant but minor result. He demonstrated mathematically that the total surface area of event horizons in the universe can never decrease. If two black holes merge, the area of the resulting event horizon is always at least as large as the sum of the two original horizons. It was a clean geometric law. But a physicist named Jacob Bekenstein noticed something deeply unsettling about it. This law, area always increases, never decreases, sounded structurally identical to the second law of thermodynamics, which states that entropy, the measure of disorder in a system, always increases. Bekenstein proposed the unthinkable, that black holes have entropy, that they have temperature, that they are thermodynamic objects. Hawking initially rejected this idea completely. It seemed absurd. A thermodynamic object radiates heat, and black holes, by definition, radiate nothing. Then Hawking did the calculation himself, expecting to disprove Bekenstein. What he found instead became one of the most important results in the history of theoretical physics. When he applied the principles of quantum mechanics to the space surrounding a black hole's event horizon, the mathematics produced something he had not anticipated. Black holes do radiate. Not perfectly, not visibly, not in a way we can currently detect, but structurally, inexorably. They emit a faint thermal glow, now known as Hawking radiation. The temperature is almost impossibly small. For a black hole the mass of our sun, it would be roughly 100 millionth of a degree above absolute
At their core,
zero.
These two extreme phenomena reveal identical
and its
underlying
implications
geometries.
are catastrophic for everything we thought we understood about black holes. If a black hole radiates energy, it loses mass. If it loses mass over a long enough timescale, it shrinks, and eventually, over periods of time so vast they dwarf the current age of the universe, it disappears entirely. This is where the story fractures, because quantum mechanics contains a law that is considered inviolable. Information cannot be destroyed. Every particle, every wave, every state of matter carries encoded within it a kind of cosmic record. Information about what it is and how it came to be. Quantum mechanics insists this record is eternal. It can be scrambled, compressed, hidden, but never erased. And yet, if a black hole swallows a star, encodes that star's information within its event horizon, and then evaporates into featureless thermal radiation, that information is gone. Permanently, irreversibly. The star's existence is erased from the record of the universe. This became known as the information paradox, and it was not a puzzle in the casual sense. It was a direct contradiction between the two most successful theories in physics, general relativity and quantum mechanics, each verified to extraordinary precision in their own domains, were producing mutually incompatible answers to the same question. Hawking initially took the most radical position available. He argued the information was simply lost, that quantum mechanics was incomplete, that nature, at its deepest level, permitted erasure. For nearly 3 decades, this was his public stance. And then, in 2004, at a conference in Dublin, he announced he had been wrong. The information is not lost. It escapes, encoded, transformed beyond recognition, buried in the subtlest correlations of the outgoing radiation. But it survives. The black hole does not erase the universe's record. It processes it. This concession, which Hawking made with characteristic precision and unusual humility, was not merely an update to a technical position. It was a statement about the fundamental nature of reality. The universe keeps its own books. Nothing that has ever existed is truly gone. The past is not erased. It is encrypted. And the event horizon of a black hole is the most extreme encryption machine the cosmos has ever produced. But Hawking did not stop there. In 2016, in collaboration with Malcolm Perry and Andrew Strominger, he proposed a mechanism for how this encryption might work, what they called soft hair. The idea was that the event horizon is not a featureless surface. Every particle that falls into a black hole leaves an imprint, a subtle zero-energy quantum excitation on the boundary itself. The horizon remembers. It stores, in a form we do not yet fully understand, the record of everything that has ever crossed it. This was one of Hawking's last major contributions before his death in 2018. And it points towards something far larger than black holes themselves. Because here is what the information paradox and its resolution actually reveals about the origin of everything. Our universe began in a state of almost perfect compression. The Big Bang was not an explosion into existing space. It was the emergence of space itself from a condition of extreme density that shares remarkable structural similarities with what we find inside a black hole's singularity. Hawking recognized this. Together with James Hartley, he developed what became known as the no-boundary proposal, a mathematical framework suggesting that the universe did not begin at a singular point in time, but rather that time itself, like the surface of a sphere, has no edge. There is no moment of creation in the conventional sense. The universe emerged the way a landscape emerges from fog, gradually, without a sharp boundary, from a quantum state that preceded the distinction between space and time. The profound connection is this: the same physics that governs what happens at the boundary of a black hole, the same equations, the same quantum gravitational principles also governs what happened at the moment the universe began. Black holes are not exotic anomalies. They are laboratories. They are the only places in the observable universe where the conditions of the Big Bang are replicated, where gravity and quantum mechanics are forced into the same room and made to negotiate. When Hawking studied black holes, he was not studying objects inside the universe. He was studying the universe's own origin,
we trace these
compressed
elements
into
back
a local
to the stellar
geometry.
nucleosynthesis that created them.
Now, the reasonable objection arrives, and it is worth taking seriously. The objection is that much of this remains theoretical. Hawking radiation has never been directly detected. The soft hair proposal is elegant but unconfirmed. The no-boundary conjecture is mathematically beautiful but not empirically verified. So why treat any of this as meaningful rather than sophisticated speculation? The answer is one Hawking himself gave repeatedly throughout his career. The history of physics is the history of ideas that were undetectable before they were detected. Atoms were theoretical constructs for over 2,000 years before we could observe them directly. Gravitational waves were predicted by Einstein in 1916 and not confirmed until 2015. The inability to measure something is a statement about our instruments, not about reality. What matters is whether the mathematics is consistent, whether it resolves genuine contradictions, and whether it makes predictions that are, in principle, testable. Hawking's work meets all three criteria. It is not speculation dressed as science. It is science operating at the frontier where our tools have not yet caught up with our equations. What black holes ultimately reveal, through the arc of Hawking's work, is something that should fundamentally alter how you understand your own existence. You are not living inside a universe that is separate from its own origins. The laws that govern this moment, the quantum rules that hold your atoms together, the gravitational geometry that keeps you on the surface of this planet, are the same laws that operated at the birth of everything. The universe did not leave its origins behind. It carries them forward, encoded in its structure, replicated in the extreme physics of every black hole that forms when a star dies. The beginning is not back there, behind us, inaccessible. It is everywhere the conditions are right. It is in every singularity. It is in the mathematics that Hawking spent his life reading. And perhaps the most extraordinary thing about that life, a man who spent 40 years unable to walk, who communicated through a single twitching cheek muscle, who was told at 21 that he had 2 years to live, is that his physical stillness became a kind of clarity. He could not move through the world. So he moved through the equations, and in those equations, he found what no telescope could show him, that the universe is not indifferent to its own existence, that it carries in its most violent and extreme phenomena the record of how it came to be, that black holes are not wounds in the fabric of reality, they are mirrors, and in them, if you know how to look, you can see the shape of everything. If you are someone who believes that understanding where we come from is not a luxury, but a necessity, if you think the deepest questions deserve the most rigorous answers, then this channel exists precisely for you. Subscribe, not for content, for the version of yourself that refuses to stop looking.